next talk we will have Mr. Angelov talking about automatic differentiation in computer graphics. And
so I'm going to talk about our implementation of automatic differentiation for GLSL. So first, a few words about GLSL itself. So most of you are probably already familiar with the language. It's usually used in frameworks like OpenGL to compute textures and generally fragment information while doing the shading pass. We also use it in ray tracing, but instead of just a second, I need to fix my screens. Okay, this is slide 2, right? So you're seeing slide 2.
Yeah.
Okay. So we have implemented a subset of GLSL in our ray tracer, and we have used it in a bit different way from the way it's used in GPUs in context like OpenGL. So typically in a GPU, the shader is run on a grid on multiple pixels in parallel and has information from the neighboring pixels. So computing the derivative of a value on a GPU in a GLSL is usually made by simply referencing the neighboring cells, so to say, for example, fragments, and just using the numeric derivative. In our case, the shaders run on intersection points. So the shader is executed each time a ray intersects a surface, for example. And in this case, using neighboring information is not very applicable. So we can't rely on a hardware implementation like a GPU, which runs through cells in parallel to give us the derivatives automatically. And there are roadblocks to using the numeric derivative. So it would be more beneficial to compute analytic derivatives. So that's what our implementation is about. And why do we need derivatives at all? Well, derivatives are used for things like texture filtering, anti-aliasing, and computing bump maps and normal maps. So most computations which rely on surface detail have some need of derivatives. So GLSL is a C-like language, but there are several constraints which make our job way easier than if we would have to implement AD for example, for C. So first, in our GLSL dialect and in the examples that I'm going to show later, we will refer to the derivative of some expression in the code by calling df(dx) or df(dy) of the given expression. That's because we only need the derivatives of those two specific global variables, x and y. Those are the screen space coordinates of the point which is currently being evaluated. If you remember, I said that the shader is evaluated on an intersection point. That's a point on some surface. So this point is represented by some coordinates on our screen. If we trace a ray from the camera to the point and see which pixel on the screen this goes through, that's the screen space coordinates. So that x and y are the variables whose derivative we need in 99% of the cases. So in our implementation, we focused on what is needed most of the time. So we have these rigorous constraints, the most important of which is that we only compute derivatives for the screen space coordinates. Also, there are some more properties of the way our GLSL dialect is built that even more facilitate easy generation of derivatives. For example, we never need the derivative of a function argument, and we never need higher order derivatives. And also in this GLSL implementation, and mostly in GLSL in particular, there are no pointers. So this saves a lot of reasoning about how we may go about differentiation. So the GLSL code will look roughly like this. We'll have some code which computes something, and okay, so the code will look roughly like this. We'll have some GLSL code, and we'll have calls to the pseudo functions df/dx and df/dy, which would retrieve which have the semantics of retrieving the derivative of the expression which is given as argument with respect to either screen space x or screen space y. So that's the setup and the task we have to solve. Now, we sort of reached the same conclusion as the colleague from the enzyme team said earlier, that trying to do differentiation on the level of AST before any optimizations is much more tedious than doing it after going into the domain of LLVM bytecode and after some of the optimizations where the code is more suited for differentiation. So we did a few attempts of trying to implement automatic differentiation on AST level, and then found out that transforming LLVM bytecode is much easier and will be the way to go. So what's being done is that after some initial optimizations, the code looks roughly like this. We have those df/dx calls translated to call instructions which call something called callback underscore df/dx, which isn't anything specific, but is used as a placeholder for the differentiation pass to replace with the actual derivative. And so after the differentiation pass, we will seek to get something like this, because in this particular case, the variable VR position is a global variable which is injected by the environment. Its derivative is also injected. And for this use case, we found out that simply having a sort of naming scheme for derivatives of given global variables, which is an extremely simple solution, works well, and the derivative pass just looks for a global variable with this prefix, and if it exists, it just uses it. So the environment is populated with known derivatives of different global variables, which are known before executing the shader. So this differentiation pass works in the following two phases. First, it goes and marks all functions which need to undergo some sort of derivative generation. For example, functions which don't have any calls to the aforementioned df/dx and df/dy calls don't need to be considered, and functions which aren't called by such functions also don't need to be considered. And so we do this marking phase beforehand to only consider functions which will benefit from insertion of derivative generation code. And also different LLVM values, well, the instructions which produce different LLVM values that are used for expressions for which we need the derivatives are recursively marked for derivative generation, so that any value which might need to have its derivative generated is marked in this pass. And later we have a second phase which does the actual insertion of derivative generation code, and it generates copies of functions which need a separate gradient computing function. I'll show you when this need arises in a few slides. And for code which needs its derivatives computed, goes over it over each instruction and inserts differentiation code. Just a second. I'll show an example. So here is some simple code which will demonstrate how the derivative computation pass works on. And so here we see that we don't work with code such as the one shown on the slide because it doesn't match the constraints I presented earlier. So that's illegal because this variable bar depends on x, which is an argument of the function. And we said that we don't compute derivatives for arguments. So let's see something else. If we have a code like this, we have a second order derivative, which is also illegal. So we don't compute derivatives for code such as this. We have df dy of some expression which contains a call to foo, which in itself has to compute the well, actually, the result of foo depends on the derivative of screen space x. So we want a second order derivative here, albeit a bit hidden. So we don't allow code like this as well. So let's see a valid example of code which we might compute derivatives for. So here we have three functions which call each other, and this function add is used in an expression whose derivative we require. So we will need to copy the add function and add a derivative computing version of it. And the function foo calls df dx in top level, so its code will need to be transformed in order to insert derivative generation. Now, the key part of this transformation is that it's just a simple forward pass of inserting derivative computation, because the variables with respect to which we compute derivatives are fixed. We don't actually need to explicitly use the chain rule. We can simply use the derivative of every single expression which is used in the computation with respect to the given global variable. So here is a transformed pseudocode. I am showing you this GLSL pseudocode instead of raw LLVM bytecode because it's far more readable. And here we see the function add, which we know that will be used in a derivative generation context, and we have copied it in the derivative generation pass in order to add some gradient computation code. And here we have added for each of the arguments another argument of the same type which encodes the derivative. You see, this is only possible because of the constraints I mentioned earlier. If we had derivative calls here inside the body of the function which call the derivative by some global variable or by the arguments, this wouldn't be possible. Also, it wouldn't be possible if we hadn't assumed that all such functions are pure with respect to x and y. So if the function uses something which depends on x or y in its body, we would need to generate separate versions for the derivative with respect to x and the derivative with respect to y, and not a generic derivative with respect to a variable t, which turns out arises very rarely in practice. Now, here we see for reference the old version of the function foo, and in the new one we have went through all the instructions and added derivative computation. So here we have a plus b, and we have added the derivative of that, which is the derivative of a plus the derivative of b. And we've done the same for the function main, where we have added code for everything, for computing the derivatives of everything.
Just a gentle reminder, we are 2 minutes off schedule.
Okay, I'll wrap up quickly. So that's generally how this transformation works. And the other important thing is that all functions and callbacks are, if there is already generated a derivative variant for them, either a specific one with respect to x, for example, as is here with this global variable, or a generic one with respect to a generic variable t, as is here, they are used. And if there is not already such an implementation provided by the environment, one is generated in the way we see here. So here is a more real-world example which calculates some sort of displacement by using a matrix which transforms camera coordinates to world coordinates and then does some arithmetic. And this results in the following LLVM bytecode, and the lines which have a red dot are newly generated by the pass which adds derivatives. So we see that we have gone through instructions, and for instructions referencing variables or functions, we have added the needed prefixes, and for loads and stores, we have simply duplicated them to do the same for derivatives. And so for calls, we have added extra arguments for the derivatives, so we don't have to apply the chain rule and don't have to do generic derivative computation. We simply can pass the derivative through an argument because we know we're calculating with respect to a single fixed global variable. So before actually going through each instruction, all operands are labeled either as inputs, outputs, or constants, and this facilitates the marking phase, which I described earlier, and is also used to determine which arguments, which operands of the instruction are derivatives and which are simply constants. For example, if we have a shuffle vector instruction, it has a constant operand, which is the specifying mask of which elements to take, and we have an input which is the actual data. So we need to keep the constant as is, and if we'll be making a copy of this instruction to calculate the derivative, we will need to modify only the input operand. So for arithmetic instructions, the transformation is straightforward. For data instructions, we generally need to copy the instruction as I described earlier and do the same thing for the derivative that we're doing for the actual operands. And for calls in global variables, we look if there's already a defined derivative in the environment, and if not, then we generate it. And if, for example, for global variables, there is nothing to generate, so the generated derivative is simply assumed to be 0. So that's the overview of the derivative generation paths which we have implemented. As I said, we have taken advantage of the very simple domain, so we didn't have to implement fully fledged generic automatic differentiation, and such a straightforward approach simply works. And I think we're out of time, and that's all.
Thank you, Angel. Questions? If not, I have a question. You said you kind of started a couple of months ago on that implementation, but do you have a raw estimate on some performance numbers? Do you have preliminary performance results on that approach?
We haven't done extensive benchmarks yet, but we have been trying to make the pass itself be as fast as possible, because actually compilation time in our use case is a bottleneck, especially for interactive renders where the user wants to change something in the scene and see feedback immediately. So instead of optimizing simply for performance of the generated code, we have also cut corners in order to keep the compilation pass fast. And we have managed to keep it well below milliseconds in most shaders which are used in the scenes we test with, but for the actual performance of the shader itself, we haven't done benchmarks apart from render time of the entire scene. We haven't evaluated the runtime of the shaders themselves as much, and render time has not been impacted noticeably, so we haven't done extensive benchmarks.
Okay, thanks again.